After understanding the necessity of the IoT platform, I will introduce the Huawei Cloud IoT Platform for you. At the beginning, let's take a look at the functional architecture of the IoT platform. There are 5 layers. We can compare it with the IoT network architecture, including the platform layer, the application layer, the access layer, which is the same as the network layer, and the device layer are the same. As I mentioned before, the platform layer functions as the bridge. It provides a service enablement layer and device connectivity layer for upper layer applications and underlying layer devices. The service enablement layer is used to centrally manage upper layer applications. It provides application APIs, data management, and a rule engine. I will talk about these functions later. This device connectivity layer checks whether IoT devices can be connected to the IoT platform. It also supports adaptation of transmission protocols. A complete IoT solution consists of 3 parts: IoT platform, and applications and devices. The IoT platform is located between the applications and the devices. It hides differences between device interfaces to enable quick device access. It provides robust capabilities to help developers quickly construct diverse IoT applications. Devices can access the platform via FBB, which is fixed broadband, and 2G, 3G, 4G, 5G, and NB-IoT and Wi-Fi networks. They can report service data to the platform using MQTT or lightweight M2M over COAP. Devices can also receive commands from the platform. Applications can call platform APIs for device management, data reporting, command delivery, and other services. After understanding the Huawei Cloud IoT solutions, let's look at the unique services provided by the Huawei Cloud IoT platform. The Huawei Cloud IoT solution provides IoT device access, IoT analytics, IoT Studio, and other related services. IoT device access provides device connectivity, device management, data forwarding, and application integration. Other related services include IoT Edge and Global SIM Link. I will explain these services later in this course. First of all, let's learn about the Huawei Cloud IoT platform from the aspect of IoT device access. In this part, I will explain device connectivity, device management, data forwarding, and application integration. This figure shows the overall architecture of the IoT device access service. At the sensing layer, we can use various access modes, such as direct device access, gateway-based access, and edge-based access. Multiple networks are supported at the upper layer. And different access protocols such as MQTT, COAP, and HTTP all can be used. Some proprietary protocols can also be used to connect devices to the cloud platform through the CIG. We will discuss about CIG later in this course. Let's look at some common IoT protocols first. The first protocol I'm going to introduce is HTTP. We are all familiar with HTTP, which is short for Hypertext Transfer Protocols. It is used to transfer data from the server to the local browser. For example, HTTP is used when we browse websites on our computers. As you can see, HTTP is a unidirectional transmission protocol. After the TCP three-way handshake, the client sends a request to the server, and the server returns a response. This protocol has obvious disadvantages in the IoT world. First, IoT devices expect to perform bidirectional transmission with upper layer applications. Second, to meet the requirement of low power consumption and wide coverage, IoT devices may not perform synchronous communications. Third, the size of an HTTP data packet is large. Due to these reasons, HTTP is more widely used as the application layer. MQTT is short for Message Queuing Telemetry Transport. It is an instant messaging protocol. MQTT adopts the publish and subscribe pattern. As shown in the figure, the client is a subscriber and the server is a publisher. The figure shows the MQTT working process. First, we need to establish a connection. MQTT runs over TCP. Therefore, when a connection is established, the publisher returns a connection response to the subscriber. According to the publish and subscribe pattern, the subscribe needs to subscribe a data, and the publisher returns a message indicating that the subscription is complete. Then, the publisher publishes a message to the subscriber. MQTT is lightweight. An MQTT message can contain only 2 bytes. MQTT also incorporates the security and reliability features from TCP. In addition, MQTT uses persistent connection, which reduces the overhead required for re-establishing connections between devices. MQTT applies to scenarios where data needs to be collected from devices and sent to servers or gateways. For example, smart home. The disadvantage of this is that it consumes more power because of its persistent connection. Therefore, MQTT is not suitable for devices that require low power consumption. To meet the needs of low power consumption, COAP is introduced. COAP is short for Constrained Application Protocol. Unlike MQTT, COAP is not reliable, and it is based on UDP in the IoT field. To make up for this, COAP provides message retransmission. COAP is also lightweight. A COAP message can be short as 4 bytes. COAP is suitable for scenarios requiring reduced power consumption, such as metering, where intelligent meter reading devices can remain in PSM mode for long periods. Now that we have learned common IoT protocols, let's have a quick look at the CIG, which is used to convert proprietary protocols. The CIG is responsible for protocol adaptation, so that devices using proprietary protocols can connect to the cloud platform. As a telecommunication equipment provider, we are good at communication on the cloud platform. Our CIG has better protocol adaptation capabilities than other platforms. It can also be deployed independently. How could independent deployment be a benefit? Many manufacturers are developing IoT platforms. Their cloud gateways may not be as good as ours. In this case, they can deploy Huawei's CIG on their own platforms to expand connections. In addition, the CIG helps us quickly build an IoT ecosystem, since it supports different protocols. Next, we will move on to the 4 functions of IoT device access. The first function is device connectivity. Devices can connect to the IoT platform using multiple protocols and access modes. As shown in this figure, the platform supports multiple access modes. For example, if a device does not have an operating system, we can use the LightOS and Access SDK to connect the device to the IoT platform. If a device does not have an SDK integrated, we can use the Access SDK to connect the device to the IoT platform. The IoT platform also supports access using native protocols, proprietary protocols, gateways, generic protocol devices, and edge devices. A variety of devices at the sensing layer can all connect to the IoT platform. The SDK used by devices to access the IoT platform is the IoT Device SDK. SDK is short for Software Development Kit. It is a software package that can help us develop software and implement specific functions. A device integrated with the IoT Device SDK can access the IoT platform. As shown in this figure, the IoT Device SDK can help directly connected devices and indirectly connected devices access the IoT platform. Devices that support the TCP/IP protocol stack can directly connect to the IoT platform after being integrated with the SDK. Devices that do not support the TCP/IP protocol stack may use protocols that cannot be directly connected to the Internet, such as Bluetooth, Zigbee, or Z-Wave. In this case, a gateway integrated with the SDK can be used to connect to the platform. There are two types of SDKs in the figure: IoT Device SDK and IoT Device SDK Tiny. So what's the difference between them? The main difference lies in their specifications and application scenarios. For example, the IoT Device SDK Tiny has a small capacity and is applicable to devices with weak computing capabilities, such as water meter, electricity meter, and geomagnetic vehicle detectors. The IoT Device SDK has a large capacity and is applicable to intelligent devices and gateways with strong computing capabilities, such as T-boxes in the IOV scenarios and smart home devices. In the previous slide, we can see that the IoT Device SDK and IoT Device SDK Tiny are connected with the gateways and directly connected devices separately, but it is not always right to say that the IoT Device SDK is used for indirectly connected devices, and the IoT Device SDK Tiny is used for directly connected devices. The applicability mainly depends on the device's capacity and the computing capability. Next, let's have a look at device management of IoT device access. Device management enables the IoT platform to manage devices and device data. We will talk first about the product model, which I will explain in detail in the next course. The product model provides key information for devices to access the IoT platform. The IoT platform records the information before accepting access requests from the devices. This is why the product model is part of device management. The product model simplifies device management for upper-layer applications and maintenance for device manufacturers. The process for connecting a device to the IoT platform has two parts: device registration and device access authentication. The device information is provided by the product model and registered on the IoT platform. The device only needs to carry authentication information to connect to the IoT platform for activation, since the device information has been registered. In addition to device connectivity, the IoT platform can deliver commands to devices. It has two ways to deliver commands: immediate delivery and delayed delivery. The two are used in different scenarios. Immediate delivery indicates that the IoT platform directly delivers a command after receiving the command from an upper-layer application. If the device is offline, the delivery fails. Immediate delivery is applicable when commands must be delivered in real time. In delayed delivery, the IoT platform queues a command and delivers queued commands when the device goes online. Delayed delivery applies to scenarios that do not require real-time command delivery. The device linkage rule in the next slide is actually the rule engine. Let's take a smart home scenario as an example. We need to set a series of linkage switches in the smart home. For example, we expect the air purifier to turn on when all the windows in a room are closed, and to shut down whenever one of the windows is open. The IoT devices themselves do not provide such a rule. We need to define this rule. The prerequisite for implementing this rule is that there is a rule engine on the cloud platform. Device linkage rules can provide many intelligent services. They are also part of device management. Device firmware upgrades and software upgrades are also part of device management. Currently, many smart vehicles such as Tesla can be upgraded in photon or SOTA mode without going to the 4S store. In OTA mode, we can remotely download software packages before upgrading the vehicle, just like for mobile phones. The IoT platform also supports batch operations. For example, we can register or upgrade devices in batches. As the number of devices managed by the IoT platform increases, it becomes time-consuming to upgrade them one by one. In this situation, batch operations can save a lot of time. The description above is all for device management. Next, let's look at data forwarding. Data forwarding enables the IoT platform to forward data to other Huawei Cloud services. As we mentioned before, the AIoT is the combination of AI and IoT. IoT can provide a large amount of data for AI, and AI can provide intelligent services for IoT. The two complement each other. This is also true for data forwarding. The IoT platform can collect a massive amount of data. Besides the IoT platform, the data can be used by other Huawei Cloud services or other third-party applications to implement full-stack data storage, computing, and analysis. The last function of IoT device access is application integration. Application integration enables industrial applications to access the IoT platform and provides open platform capabilities to applications through the APIs. I will focus on application integration in the next course. Now, I will introduce a few important APIs for you. First, application registration authentication. Both devices and applications must be authenticated before they can access the IoT platform. An application must obtain a token from the IAM service and then use the token to call platform APIs. Next one is subscription to device information. This figure shows an example of common API calling. Of course, there are many API callings on the application side. I will explain them in the next course. An application calls an API to subscribe to the IoT platform, and then the IoT platform will send data reported by the device to the application.